magnetic field due to a loop. So I did this video, and I derived this. The magnetic field due to a loop of wire of radius r, current I, calculate the magnetic field. Did it. Okay. And we also did it numerically. We took a little loop, broke it into a bunch of little bitty tiny little pieces of IDL, calculate the magnetic field due to each piece, and then added them all up. And I did that. But what I want to do is to take that program, which I'm going to show you right now, and just make it better. So I want to display the magnetic field in a lot of different places around that loop. And then after that, I'm going to show you how to calculate the same magnetic field using the dipole, the magnetic dipole moment for that loop. Let's get started. So this is the code that we had before. I'm going to go ahead and run it, and then I'll tell you what's there, and then we're going to have to change it. So this just calculates the magnetic field at one particular location. So here's my loop. Oops, that's too big. Here's my loop of, I think, that's 30 or something different wire segments. Each one of those has an IDL, and then I use that IDL and the observation location, which is right there, to calculate the individual magnetic fields and add them all up. It works great. Agrees with theory. But I can put this anywhere. Okay, so we want to do a couple things. Number one, I want to make a function that calculates the magnetic field anywhere instead of doing it just as one loop. I want to make a function, so I just give it a location, gives it back to me. To do that, I need to actually add all these things as a list, and then I need to pick all my points. So we got a lot of work to do, but it's going to be great. Trust me. So the first thing I'm going to do is to make this a little bit smaller. How big did I make this before? Because I want to look at a larger region, and these numbers don't matter, but I'm going to put this at 0.1 just to make it smaller. Okay, that's all I'm going to do right there. Now down here, what I want to do is, so let's just go through what's going on so far. So I have this angle theta, and I break it into 30 pieces, and I just angle my way around there to calculate the little path length each time. And while I do that, I call this Ri the vector position of the current, and then dl is the axis for that current. And then I use that to calculate the magnetic field. All in one loop, but I want to break it into two loops. Okay, so to do that, let's get rid of this b. Don't need that. Let's go ahead and add a list of the elements I'm going to add to that. So that's all I want to do first, is just add all my elements up. Okay, so I don't even need that sphere. I don't want that. So while this is all good, I'm going to make that. This DL, let's just get rid of DL. No, let's call it DL. But then DL, let's get this arrow part right here. That's what I want to do. LS equals LS plus an arrow. And that arrow has my position and the axis. The axis is the DL. Okay, so I'm just going to put right here, bracket. So now I have a list of things. Now right here, I don't actually need to do this. Let's just comment this stuff out. I can do this later. Comment out, data is increased. Okay, so this other stuff, let's just get rid of. Oh, I'm going to leave B-scale in there. Oh, what the heck is happening? Okay, B-scale I can leave, but this stuff I'm going to delete and delete this. And let's run it just to make sure things are working. It should just make my arrows. There. Okay, so that's working. Now I can define a function that calculates the magnetic field anywhere. So let's do that right down here. Def B ROT. So this is a function B. I'm going to pass to it an observation location, and it's going to give me the total magnetic field due to that loop. So to do that, the first thing I need to do is to have a temporary magnetic field of 0, right? Because I'm going to add up the vector due to each individual piece, but I have to have something to add it to, so that's what this is. Now I can go through my list. So for, I'll call it DLS in LS. So the DLS will be those arrows in that thing. And I don't really care about the arrows, but I care about the position. I care about the axis, and that's what I'm going to use. Okay, so in that loop, I'm going to call each one DLS. So I'm going to first calculate R. I'll call it, this is called R. It's going to be ROT minus DLS.POS. So that's the vector from my particular location to where I want to calculate the magnetic field, and that's my R. Now I can go ahead and calculate dB. dB is going to be, I'm going to write this out as mu naught divided by 4 times pi times I dl, so I'm going to say I, times cross product of dl. So dl is dls, this kind of looks weird, dls dot axis. Right? That's my length of my thing. It has the direction and the length. It's all built in there. And I want to cross that with r. And then I'm going to divide all of that by the magnitude of r cubed. And you can't see that. Right there. Now I can take that and add it to the total. So BT is BT plus dB, and I'm done. Return BT. Let's just see if it works. Do I already have an observation location? Yeah, RO. So let's say print B at RO. Let's just see if it works. I know it should be in the Z direction. Yeah, so that looks right. So that's 0, 0, Z direction. That's good. You know, I kind of want this. I'm going to make a change. I want my coil in the XY plane instead of the in the XZ plane. It's just going to look a little bit better. So let's rotate this. I'm going to get rid of this because I don't want to print something weird. So I'm going to rotate this. All I have to do is to change my up here. I can just put 0. I think this will work. If I destroy things, I'm going to be very mad. And then get this, put the 0 right here. I'm just moving the Y to the Z. And then the same thing over here. 0, comma. Get rid of that. I think that's all I need to do. Let's just try it. It shouldn't calculate anything, but it should be. Is that right? There we go. Okay, good. Now, that's fine. Let's just leave it like that. Now we're ready to roll. So what I want to do is to create a whole bunch of points in the XYZ plane space and calculate the magnetic field at each one of those spots and draw an arrow. That's what I want to do. Okay, so we've done this before. I've done this many times. Let's just do it again. Now, I played around with this. I'm going to use n is equal to 8. And I'm going to say L is equal to 1. So I want a 1 by 1 by 1 box of points. And remember, my ring has a radius of 0.1, so it should be fine. ds is going to be equal to L over n. This is the step size between all my pieces, right? I need to know that. And then I need to have a start location or vector where I'm going to move around. So say RS is, I'm going to start at the very bottom negative corner. So it's going to be vector negative L over 2. No, L over n. Right? Yeah. No, L over 2. Yeah. Plus ds over 2. So, you know, you don't have to do that, right? But I'm going to shift it over so it's in the middle of my little space. And then I'm going to have the same thing in the X, Y, and Z direction. So I'm going to copy this, and I'm going to say paste, comma, paste. So that's where I'm starting my little square adventure. Now I'm going to say while rs.z is less than L over 2, while rs.y is less than L over 2, while rs.x is less than L over 2. And so I'm going to go in the X, Y, and Z direction like that, a triple loop. Now at the beginning of the Y, before I do the Y loop, I need to reset rs.y is equal to negative L over 2 plus ds over 2. Right. I don't know why I'm getting ds over 2. Yeah, that's right. Okay. And then when I repeat the X loop, I need to say y rs.x is equal to negative L over 2 plus ds over 2. And then I'm all set. So right here in the X thing, I'm going to go ahead and just draw a sphere. So let's just put a sphere there. Position is going to be equal to RS. Radius is going to be equal to L over 100. You know, we can change that later. We just want to make sure that we're making our points right. And then I'm going to increase my value in the x direction. So rs equals rs plus vector ds 0, 0. And then that's going to finish that loop. And then I'm going to repeat this in the y direction. Rs equals rs plus vector 0 ds 0. And then I'm going to repeat this in the z direction. Rs equals rs plus vector 0, 0 ds. Be careful, right? Because these are the places where if you don't do things right, you're going to end up with the infinite loop. And infinite loops take a long, long time, and they're awkward. Okay, so hopefully I didn't do that. But if I did, you'd never know because I probably wouldn't post this video. Let's save. I didn't even save this. Let's call this B loop visual. Save. And I'm going to run it. So we should just get a bunch of spheres. Boom. There. Okay, so now we're working there. There's my coil right there in the middle, and there's all my points. 8 by 8 by 8. You can do 10 by 10 by 10. Don't do 20 by 20 by 20 because, you know, it's raised to the third power, so that's kind of bad. Up here, I can do this. I want those to look a little bit bigger, so I'm going to put this thing called, let's see, let's scoot this over. Shaft width. Shaft width equals 0.01. I'm not sure what the value should be, but let's just try that. I want it to, there. Now it shows up a little bit better. I actually don't even care about the spheres. I'm not going to put the spheres there, but what I want to do is calculate the magnetic field at each one of these locations and make an arrow. So going back down here, instead of drawing a sphere, I'm just going to comment that out, and I'm going to put arrow. I'm not even going to give it a name. The position is going to be RS. The axis is going to be B scale, which, did I have that capitalized or not? Did capitalize. B scale times B of RS. So remember, B returns a vector at that location. What color should this be? It should be cyan. I don't know, I'm just picking cyan. Color equals color dot cyan. Let's run it. Okay, isn't that great? So you see here a problem in that I calculate the magnetic field, but when you get super close, you get super big. So what I'm going to do to fix that, I'm going to plot the unit vector of that magnetic field so they're all the same length, and it'll give us a better idea of the shape. I think it just looks better. You could do a whole, you could say if the magnetic field's too big, just don't plot it or something like that. But I'm actually going to calculate the magnetic field and then take the unit vector in that direction. Okay, now they're too big, right? But they're all the same size. Well, that's fine, I can fix that. Let's put this B scale at 0.1. Let's just try that. Okay, that looks pretty good. I want a little bit smaller. So 0.7. I think that's pretty good. There's my magnetic field. So see, if you have too many points, and this one may be too many, then it looks too cluttered. And in fact, in this case, I might want to do like a shaft width on there. You can play around with this and make it perfect as you like. Let's try a smaller shaft width. Let's say shaft width. You can't see that. Okay, hold on. Shaft width equals 0.01. Let's just try that. Not sure what that did. Let's make it a little bit smaller. Also, if you misspell shaft width, it doesn't do anything. Shaft width, that's fine. Let's just put 0. Let's just try that. That's going to be, hopefully that should be way too skinny. Yeah, but it looks good. So let's just increase that a little bit. And this is the art style, the part of physics. Let's put this at 0.5. I think that should be good. Okay, I'm pretty happy with that. So there's your magnetic field due to that loop. And so this isn't a numerical calculation based on these 30 pieces, but you do notice that we get this same dipole moment-like thing as we did for an electric dipole, right? It kind of looks the same way. So we can calculate the dipole moment of this loop and then use the dipole moment to plot the magnetic field and make a comparison. So let's switch over here to the board. and talk about the dipole moment. So we can calculate the dipole moment, the magnetic dipole moment M, as 1/2 the sum over I, Ri cross I dLi. That looks dumb because I used a derivative there. I say it should be delta I guess. So that's very similar to how we calculate the electric dipole moment as a sum of RQ, but now we have to do the cross product, right? So it's going to do this thing. Is that right? Yeah. And then once we have that dipole moment, we can calculate the magnetic field using M, and this looks just like the electric field due to a dipole, except it's magnetic. Mu naught over 4 pi, 3 times M dot R hat times R hat minus M, all of that over R cubed. So what we want to do, number one, calculate the dipole moment. Number two, use this to plot the magnetic field at all the locations and see how they compare. Okay, so this way we don't have to do a loop around the whole thing. We can do a whole bunch of different stuff to calculate the dipole moment, and that's what we're going to do. So let's go calculate the dipole moment. Up here, I'm going through the whole thing, right? I can just calculate the dipole moment here. So here I'm going to say M is equal to vector 0, 0, 0, because I want to add to it. It's a sum. Down here, let's just go and say M equals M plus Ri cross I dl. So it's going to be the location, which is Ri, cross product, Ri, and then I times dl. So dl in this case is just that vector dl. And that's it. So I have my magnetic dipole moment. Now let's make another function right here. I'm going to say def bm, like that. And I'm just going to calculate the dipole moment due to that magnetic moment. You could do it in one case. I'm going to do this. As a temporary thing too. So bt equals mu naught divided by 4 times pi times 3 times the dot product of m norm ROT. Let's look at my formula right here. And then I have to multiply that by norm ROT, and then you can't even see that. And then I need to take all of that and subtract m. And then divide by the magnitude of ROT cubed. And then I'm going to return BT. I just assume it's going to work. So down here, when I go through my loop and I make that arrow, I'm going to make another arrow. This other arrow, the position is going to be the same thing, RS. The axis is going to be equal to B scale times norm BMRS. And then the color, color equals color dot magenta. Can't spell that. And then shaft width is the same. Shaft width equals 0.005. Let's see if it works. Run it. There we go. It did work. And it looks really great. So you'll notice, let's zoom in over here, when we're really close to this, this loop, we have these two arrows that do not agree, right? So the magenta ones are based on the dipole moment, which is an approximation. It's not an actual dipole, it's a loop. So the cyan ones are based on the 30 little ILs, so it's very much closer to being correct. Now, as I move further away over here, you can see these arrows, they're pretty much identical, right? So as you get further and further away, that approximation of a dipole moment works. But there you go. Look at that. That's your physics to art right there. I'm trying to find the best angle for that. This is going to be the best thumbnail. Okay, so there you go. The dipole moment of a loop of wire, very important, because just like with electric fields and electric matter, we represent things as dipole moments. We're going to use dipole moments in magnetic fields too. This code is down below if you have any questions. The playlist for this whole thing's down below, so you can find my previous video where I calculate the magnetic field due to a loop. But that is that. I might make one more video, but I'm not sure. Talk to you later.